Hello, welcome back once again. Now let's look at the non-homogeneous second order differential equations. These are equations of this form: a d squared y over dx squared plus b dy over dx plus cy is equal to g of x. This equation is non-homogeneous. Previously we looked at how to solve homogeneous. So to solve this type of differential equations, this type of equation has got two solutions. Has got the general solution of this equation. The general solution is of this form: y shall be equal to the general solution plus a particular solution. General solution, let G represent general solution and Pi to represent particular solution. So to get the general solution is obtained by getting the homogeneous solution. Homogeneous solution of that equation. You get the homogeneous solution, that one will give you the general solution. And how do you get the homogeneous solution? We take the equation as dy squared over dx squared plus b dy over dx plus cy, we equate it to 0. If this equation is equated to 0, this one is now homogeneous. So this solution of homogeneous is what shall give us GP. And we know that this GP is actually equal to 0. After getting this solution, we add to the particular solution. Let's have our particular solution to be, let's say, j of x to be the particular solution. So such that y shall be equal to the homogeneous solution, that is h of x, plus the particular solution may be j of x. We know that, so our y shall be equal to, from that corresponding, our y shall be equal to h plus j of x, which can be expressed as y to be equal to h when y is to the second derivative plus h y to the first derivative plus cy. Let's plus, now let's add the particular solution, that is j first second derivative plus j first derivative plus jy to be equal to g of x. But we know that this is from the homogeneous solution that was equal to 0. So it is this part that gives us the particular solution that is equal to x. So we are going to use this general solution to practice. So let's have an example. So let's have this example. Y double prime minus 3y prime minus 4y is equal to 3 exponential of 2x. This one, first we get the general solution by getting the homogeneous equation, that's by equating y double prime minus 3y prime minus 4y to be equal to 0. This one shall be our now homogeneous equation. So we solve this one by the d operator method. That is, we solve this one, that shall be, let's have our variable to be r squared minus 3r minus 4 is equal to 0. Let's get the root of these equations. This equation can be found. Look for two numbers that if you multiply them you get negative 4. If you add them you get negative 3. That one shall have r squared minus r minus 3r, r plus 4r minus 4 to be equal to 0. Such that, plus r minus 4r, such that if you add r plus negative 4r, you will get negative 3r. So if you factor out within the first two terms, r is common, r plus 1. And in this one, it goes, what for negative 4 is common, negative 4 goes here, r, then plus 1. So the two brackets are same, so you can factor r minus 4 into r plus 1 to be equal to 0. So it means that r is either 4 or r is negative 1. So from the homogeneous, we have got two distinct real roots. So if the roots are distinct and real, the y as a general solution of the form a exponential of mx plus b exponential of alpha x. So this one shall give us a exponential of our first one to be 4x plus b exponential of negative x. So this is our general solution. That is the general solution. But we know very well that this one is actually equal to 0. So let's get the particular solution. Particular solution, you get it from the equation that was y double prime minus 3y minus 4y is equal to 3 exponential of 2x. So by using the method of undetermined coefficient, we look by the method of undetermined coefficient. We look for a number whose differentials, when summed together, you will get a number of this form. So we take any anonymous number whose differential will give you exponential. And from the tables of derivative, we know that if you differentiate an exponential, its coefficients comes down. So let's have the number as, since the power of the exponential does not change, you have the number as an exponential of 2x with a certain coefficient. Let's have it as a. Let this one to be equal to your y. If y is equal to that one, what will be y prime? Y first prime will be 2a exponential of 2x. Y double prime shall be equal to what? 4a exponential of 2x. So after having all these parameters, we substitute it in this equation for us to get the particular solution. So let's substitute as here. If we substitute, we shall have, you bring the y double prime, that is 4a exponential of 2x minus 3 into y double prime, that is 2a exponential of 2x, then minus 4y, which is a exponential of 2x, to be equal to 3 exponential of 2x. So if you expand the brackets, you get 4a exponential of 2x minus 6a exponential of 2x minus 4a exponential of 2x to be equal to 3 exponential of 2x. So we can divide all through by exponential of 2x. This side also by exponential of 2x. We get that 4a minus 6a minus 4a to be equal to 3. So this and this cancels out. You get negative 6a to be equal to 3. Our a shall be equal to negative a half. So after getting the negative a half, you replace in the preempted solutions. That's y shall be equal to, we found the value of a to be negative half exponential of 2x. So this is our particular solution. And we know that we have preempted that general solution is in the form of general solution plus the particular solution. So our y shall be equal to, the general solution we found to be a exponential of 4x plus b exponential of negative x. Then we now add the particular solution, that is minus a half exponential of 2x. So this one is now our general solution. So if given the boundaries, you can get the value of a and b. So in our next example, we shall do one with the boundary so that we get the values of a and b for us to get the specific solution of the second order differential equation by the method of undetermined coefficients. Thank you.